When people hear the name Linux 7.0, it immediately sounds like a massive leap forward, a dramatic new chapter in the story of open-source computing. But here's the truth that many casual users don't realize. There is no single operating system officially called Linux 7.0 in the way we talk about Windows 11 or Mac OS Sonoma. Linux itself is a kernel, originally created by Linus Torvalds back in 1991, and over the years it has evolved through thousands of versions. What most people refer to when they say Linux 7.0 is usually a major version of a specific Linux distribution, not the kernel itself. That distinction is incredibly important because Linux is not one product. It is an ecosystem. It is a foundation. It is a core that powers servers, supercomputers, smartphones, embedded devices, and even spacecraft. So when we talk about Linux 7.0, what we are really discussing is the evolution of that ecosystem and how major version jumps in distributions signal long-term stability, enterprise readiness, performance optimization, and strategic shifts in the open-source world. To understand what Linux 7.0 could mean, we first need to understand what Linux truly is. At its core, Linux is the kernel, the part of the operating system that communicates directly with hardware. The kernel manages memory, processes, drivers, file systems, and networking. Everything else that users interact with, whether that is a desktop environment like GNOME or KDE, a package manager like a PT or a DNF, or a shell like Bash, sits on top of that kernel. Over the decades, the Linux kernel has progressed from version 1.x to 2.x, then 3.x, 4x, 5.x, and now 6.x. Version numbers in Linux do not necessarily represent revolutionary changes in the same way commercial operating systems market their releases. Instead, they mark ongoing development, incremental improvements, and structural refinements. So the idea of Linux 7.0 as a kernel version would represent a milestone in stability. Architecture updates, hardware enablement, and possibly major internal rewrites. However, when people say Linux 7.0, they are often referring to a distribution release like Red Hat Enterprise Linux 7, CentOS 7, Oracle Linux 7, or other enterprise-focused platforms. Enterprise Linux version 7 marked a huge turning point in business environments. It introduced modern system management tools, improved virtualization, better container support, stronger security defaults, and extended long-term support cycles. These version jumps often last for a decade or more in enterprise support, making them incredibly significant for data centers, cloud infrastructure, and corporate IT departments. Let's imagine Linux 7.0 as a next-generation release, representing a modern era of Linux evolution. One of the biggest areas of advancement would be hardware support. Linux already supports an enormous range of devices, from ARM-based systems to x86 servers and RISC-V development boards. A Linux 7.0 generation would likely include enhanced support for next-generation CPUs, GPUs, AI accelerators, and advanced storage technologies. With the rise of artificial intelligence and machine learning workloads, kernel-level optimizations for tensor processing units and neural compute engines would become more refined. We would see improved scheduling for heterogeneous computing environments where CPUs, GPUs, and AI accelerators work together seamlessly. Security would be another defining theme. Linux has always been considered secure compared to many proprietary systems, but modern threats demand continuous evolution. Linux 7.0 would likely strengthen secure boot mechanisms, mandatory access control frameworks like SI-Linux and APARMor, and kernel-level isolation technologies. Containerization has already changed how applications are deployed. With tools like Docker and Kubernetes dominating cloud infrastructure, Linux must maintain superior namespace isolation, groups management, and minimal attack surfaces. A major version milestone would reflect stronger defaults, zero-trust architecture integration, and enhanced encryption standards across the board. Performance optimization would also define Linux 7.0. The kernel scheduler would continue evolving to better distribute workloads across multi-core and multi-threaded CPUs. Memory management would improve for high-density cloud systems running thousands of containers simultaneously. File systems like ext4, XFS, and BTRFs would see refinements in journaling, snapshotting, and scalability. Networking stacks would optimize throughput for 100 gigabit and even 400 gigabit network interfaces. Latency reductions would benefit high-frequency trading systems, gaming, streaming, and edge computing environments. Another major shift would revolve around cloud-native computing. Linux already dominates the cloud. The majority of servers running on AWS, Azure, and Google Cloud rely on Linux distributions. A Linux 7.0 generation would double down on container-first design. It would integrate better orchestration hooks, improve kernel features like eBPF for observability, and enhance system telemetry. eBPF has become one of the most transformative technologies in modern Linux. It allows developers to safely run sandboxed programs inside the kernel for monitoring, networking, and security without modifying kernel source code. A new era Linux release would expand eBPF capabilities even further, making performance tracing and real-time analytics more efficient and secure. Desktop Linux would also evolve significantly. Although Linux dominates servers, desktop adoption has been steadily rising, especially among developers, gamers, and privacy-conscious users. With the growth of projects like Proton, which allows Windows games to run on Linux, gaming performance has improved dramatically. GPU driver support from companies like NVIDIA and AMD has become more stable and feature-rich. A Linux 7.0 ERA desktop would likely feature smoother Wayland adoption, better fractional scaling, improved HDR support, and enhanced power management for laptops. Battery efficiency on modern hardware would improve through kernel-level tuning and smarter CPU frequency scaling. Another transformative aspect would be support for new architectures like RISC-V. As open hardware gains momentum, Linux plays a central role. A Linux 7.0 milestone would likely include optimized support for RISC-V platforms, enabling more commercial devices to ship with fully open instruction sets. That would have profound implications for sovereignty, custom silicon design, and regional technology independence. Artificial intelligence integration would also shape Linux 7.0. The operating system would not just run AI workloads, it would optimize them. Kernel scheduling could become more AI-aware, prioritizing tasks based on workload classification. Power management algorithms could adapt dynamically based on predictive models. Security monitoring could incorporate anomaly detection directly into system logging frameworks. Storage innovation would be another pillar. NVMe drives, persistent memory technologies, and distributed file systems are becoming standard in enterprise data centers. A Linux 7.0 generation would refine how the kernel interacts with ultra-fast storage. Reduced overhead in I/O stacks, better caching algorithms, and enhanced multi-queue scheduling would ensure maximum throughput with minimal latency. Networking would continue evolving towards software-defined infrastructure. Linux already powers routers, firewalls, and telecom equipment. With 5G and eventually 6G deployments expanding globally, Linux kernels must handle massive packet processing loads. Advanced traffic shaping, kernel bypass technologies, and programmable networking frameworks would be refined in a Linux 7.0 era. The user experience for administrators would also improve. Modern Linux distributions focused heavily on automation. Tools like systemed revolutionized service management. Future iterations would continue refining boot processes, dependency handling, and resource tracking. Automation frameworks would integrate more tightly with configuration management systems like Ansible and Puppet, reducing manual overhead in enterprise deployments. Energy efficiency is another crucial topic. Data centers consume enormous amounts of electricity. A Linux 7.0 generation would likely prioritize green computing. Smarter CPU scheduling, improved idle state management, and better workload consolidation would help reduce carbon footprints. Edge devices, IoT systems, and embedded Linux deployments would benefit from micro-optimizations designed to stretch battery life and reduce thermal output. Compatibility and backward support would remain core strengths. One of Linux's biggest advantages is stability. Applications compiled years ago often continue to run on modern systems. A major version milestone would ensure that legacy enterprise workloads continue functioning without disruption, while still offering new features for modern applications. Developer experience would also be central. Linux is the platform of choice for programmers worldwide. Toolchains like GCC and Clang would be updated to support new language standards. Debugging tools would become more powerful. Virtualization technologies like KVM would improve nested virtualization and hardware acceleration support. Containers would become lighter and more secure through rootless operation and improved namespace isolation. Community governance would remain fundamental. Linux thrives because of global collaboration. Thousands of contributors submit patches, review code, and test features. A Linux 7.0 milestone would represent years of cooperative engineering across continents. Companies like IBM, Intel, Google, and countless startups would continue investing in kernel development, ensuring that Linux remains adaptable and competitive. Education and accessibility would also expand. Linux distributions are widely used in universities and research labs. A new generation release would likely simplify installation processes, improve accessibility tools for users with disabilities, and enhance documentation clarity. Localization efforts would continue, making Linux more accessible in developing regions. In cybersecurity, Linux 7.0 would likely enhance kernel lockdown modes, mitigate speculative execution vulnerabilities, and improve memory safety features. With the increasing importance of supply chain security, package verification systems and reproducible builds would gain prominence. Embedded systems would not be left behind. Linux powers smart TVs, routers, industrial controllers, and automotive infotainment systems. Real-time kernel improvements would benefit robotics and manufacturing automation. Automotive-grade Linux systems would become more robust and responsive. Another important dimension would be interoperability. Linux increasingly coexists with Windows and macOS in hybrid environments. Improved file-sharing protocols, better Active Directory integration, and seamless virtualization compatibility would strengthen its position in mixed infrastructures. From a philosophical standpoint, Linux 7.0 symbolizes maturity. It reflects decades of refinement, community trust, and industry adoption. Unlike proprietary systems driven by single corporations, Linux represents collaborative progress. Its version milestones are not marketing events, but technical achievements. Looking forward, Linux 7.0 would likely represent convergence. Cloud computing, edge processing, artificial intelligence, IoT, and desktop computing would increasingly rely on shared kernel improvements. Rather than fragmenting, the ecosystem would unify around scalable, secure, and efficient foundations. In conclusion, Linux 7.0 is less about a single product and more about a stage in evolution. It represents stronger hardware support, tighter security, optimized performance, deeper cloud integration, improved desktop experiences, AI acceleration, and energy efficiency. It reflects the ongoing journey of open-source collaboration that began with a simple announcement on an online forum in 1991 and grew into the backbone of modern digital infrastructure. Whether powering data centers, enabling gaming on desktops, running smartphones, or driving supercomputers, Linux continues to evolve. A milestone like Linux 7.0 would not just be a number change. It would be a testament to decades of innovation, resilience, and community-driven progress that shapes the future of computing worldwide.